In this video, we're going to talk about the division algorithm for polynomials. But before we even get into polynomials, let's talk about the division algorithm for integers. So just as a reminder, here's the division algorithm for integers. That's a theorem that states that if a and b are integers, and b is greater than 0, then there exist integers q and r such that a is equal to bq plus r, and 0 is less than or equal to r is less than b, the number being divided by. And these integers q and r are unique to a and b. So in other words, if I pick two integers, a and b, a is the number I'm going to divide, and b is the number I'm dividing by, and the number I'm dividing by is greater than 0, then I can find some integers q and r, which we call a quotient and a remainder, such that a is equal to bq plus r, and the remainder is relatively small. In other words, it's smaller than b, and it's still non-negative. And in fact, there's a unique quotient and remainder that will satisfy those conditions. All right, but sometimes it's easy to look at this and miss out on the fact that division appears nowhere in this sentence. There's nothing in this sentence that directly mentions division. So why in the world is this about division at all? Well, in grade school we learned to divide integers like 378 and 4, and we would divide by saying, well, 37 divided by 4 is 9 plus a little bit, so we know we can take 9 full 4s out of 37. 9 times 4 is 36, so then we subtract and we get 18, and then 4 goes into 18 4 times. 4 times 4 is 16. We subtract 16 and get 2. And so therefore, 378 divided by 4 gives us 94 with a remainder of 2. But what does it really mean when we're doing that? When we interpret this result, we understand that this means that if we divide 378 by 4, then we get 94 4s and an additional 2 left over. In other words, 378 can be expressed as 4 times 94 plus 2. So that's my A, that's my B, and then this is my quotient, and this is my remainder. What those quotient and remainder are saying is that 378 consists of 94 4s, 94 groups of 4, plus an additional 2 left over. But now the thing I want to think about is, what if we didn't have this algorithm which we learned in grade school? What if we just asked ourselves, we have 378 of something, we want to package as many 4s as possible out of that, and figure out how many packages of 4 we can get, and how many items, if any, we'll have left over. And we don't have any algorithm like this, any standard algorithm that we learned in grade school. How would we approach that problem? Well, let's just come over here and think about it. So if I have 378, and I think, how many 4s go into 378? Well, one thing I might start by doing is I might think, are there any multiples of 4 that I can come up with that are pretty close to 378 that could be taken out? Because if I could just think of a large number of packages of 4 all at once and take those out, that would simplify this problem greatly. And one thing I think of is that 360 is a multiple of 4. 360 is 4 times 90. So I'm going to imagine myself taking out 90 packages of 4, 90 times, and I'm going to draw a little bag here. I'm going to take that out of my big box of 378. So these come out, and what's left? I'm left with a box with only 18 items remaining. All right, so symbolically we can represent that by saying, well, 378 minus 4 times 90, so 90 little packages of 4 is 18. Or in other words, 378 minus 360 is 18. All right, so now I've got 18 left, and I think, how many more packages of 4 can I take out? And I know that 16 is a multiple of 4 that's pretty close to 18, and that's 4 times 4, so I'm going to take out 4 more packages of 4, so little bags of 4 items. And I think I'm left with only 2 because I'm taking out 16 from 18. That leaves me with a box of only 2. So in other words, if I subtract another 4 times 4, I'm going to be left with 2. Or down here I might say minus 16. That gives me 2. And at each step of this process, I can record the number of little packages of 4 that I'm forming. So I've got 90 bundles of 4 here, and I've got 4 bundles of 4 here. If I just take a look at that work, and contrast it with the work that we have over here in the standard algorithm. So if we move over here, zoom out a bit, and then look at the work over here, I think you'll see a lot of similarities. You see that remainder here, and you see the remainder of 2 here. You see us keeping track of how many little bundles of 4 we're taking out. Here, it's a little bit more compact. And you see at each stage, we're taking out all of those bundles of 4 in order to figure out how many we have left. It's just in the standard algorithm, we keep track of that number that we're taking out here is 36, not 360, but that 36 really represents 360, and the 9 we wrote down here really represents 90 bundles of 4, not just 9 bundles of 4. So that's a little story about how we end up with this standard algorithm for division. It can all be thought of in terms of taking out bundles of the number you're dividing by. Now for polynomials, things are a little bit different because the idea of how many can we take out is somewhat less intuitive when that number is represented in terms of x's or in terms of variables. But the idea is the same. So let's suppose I want to divide this polynomial, x cubed minus 4x squared plus 7x plus 11 by, let's say, x minus 5. All right, so I want to figure out how many times, and I'm going to put that in quotation marks because that's a really wobbly concept here, but we are kind of thinking how many times does x minus 5 go into, again in quotation marks, go into x cubed minus 4x squared plus 7x plus 11. But in this case, our interpretation of how many times does this go into is much more algebraic. So what we're really looking for is we're trying to write x cubed minus 4x squared plus 7x plus 11 as some multiple of x minus 5. So this times some polynomial q of x, and that's going to be called our quotient. And then some hopefully small remainder from which I can't take out any more little bundles of x minus 5. So these represent our bundles of x minus 5, and these represent what's left. So let's see if we can attack this problem using the same primitive technique that we have over here. I know that you may come into this course knowing a division algorithm for polynomials already, but I want to show how we can develop that using the same basic algebraic idea that we used over here with the integers. All right, so let's try doing this just using the same iterative approach. So I have x cubed minus 4x squared plus 7x plus 11. And I'm going to start just like I did with 378 by thinking of a multiple of x minus 5 that is kind of close to this that I could take out and leave myself with a smaller remainder. So what multiple would that be? Well, what can I multiply by x minus 5 that would give me something useful to take out over here? Well, I'd really like to get an x cubed to take out because then I'd be left with only a quadratic over here. And to get an x cubed over here, I'm going to multiply this by x squared. And if I do that, I get x cubed minus 5x squared. All right, so let's see what happens if I take out x minus 5 times x squared. So I'm going to be taking out x cubed minus 5x squared. What does that leave me with? Well, I'm subtracting negative 5x squared from negative 4x squared. I believe that leaves me with x squared. I've got 7x plus 11. Okay, so now I think, what is another useful multiple of x minus 5 that I could take out? Well, if I take x minus 5 times x, that'll give me a term of x squared. In fact, that gives me x squared minus 5x. So if I subtract x squared minus 5x, so again, what I'm doing is I'm subtracting x minus 5 times x. then that's going to give me, I believe, 12x plus 11. All right, so now what useful multiple of x minus 5 could I take out now? Well, I could take out x minus 5 times 12. That would give me a term of 12x. And, well, 12 bundles of x minus 5 is 12x minus 60. So subtracting 12x minus 60, what does that give us? So again, just going to notate over here, I'm taking out x minus 5 times 12. And it looks like I will get, I'm subtracting negative 60 from 11, so that's 71. And at this point, I think, okay, what other useful multiple of x minus 5 could I take out? And at this point, I realize that if I multiply anything, any polynomial by x minus 5, I'm going to get at least an x in there, at least a linear term, if not more. And I really just, I don't want to muddle this anymore. I don't want to muddle this by reintroducing variables. 71 is kind of a nice small thing to have left over in terms of polynomials. It has no variables, it's constant. So I think this is where I'm going to stop. I'm going to stop with a remainder of 71. But let's interpret the result we've come up with here. So what we've shown is that x cubed minus 4x squared plus 7x plus 11 minus some very large multiple of x minus 5. Because we ended up taking out x squared times that, and then x times that, and then another 12 times that, and that left us with a remainder of 71. So moving all of this to the other side, we can say x cubed minus 4x squared plus 7x plus 11 equals x minus 5, that's my divisor, times x squared plus x plus 12, that's my quotient, q of x, plus 71, that's my remainder, r of x. And you'll notice the degree of r of x ended up being less than the degree of the polynomial I divided by, in this case, x minus 5. So now we can encode this entire process in an algorithm that uses a standard notation and gives us a standard shorthand for representing the steps that we're doing. By the way, when I say standard, it doesn't mean that this is the only standard that you can come up with. It's just, it happens to be standard because this is what we've done for a very long time. So anyway, let's go ahead and start the same way we did with integers. Let's draw a big box here. And this box is going to contain x cubed minus 4x squared plus 7x plus 11. Our divisor will be x minus 5. By the way, the terminology here is the thing I divide by is called the divisor. The thing that I am dividing is called the dividend. Let me write those down. Divisor, dividend, because that's the thing to be divided. And then, of course, I'll have my quotient and remainder after I'm done with this process. So what do? Well, we start the same way we started over here. We identify some multiple of x minus 5 that would be useful to take out. We know that x times x squared would give us x cubed. So we notate an x squared over here. And traditionally we put that here, but as long as you keep track of what you're multiplying by the divisor, you can put it wherever you want. I like putting it there. X squared times x minus 5 is x cubed minus 5x squared. Subtracting that will give us x squared. And I usually put a subtraction sign over here. And then I even put parentheses here just to remind myself I'm subtracting that entire thing, which means I need to subtract both terms and not add the negative 5x squared. I'm left with x squared plus 7x, and I don't write down the plus 11 because I think the next step is going to condition only on what I have written here now. But x times x gives us x squared, so I'm going to have an x here. I'm going to multiply that x by x minus 5, get x squared minus 5x. Subtracting that gives us 12x, and now I carry down the 11. X times 12 gives me 12x. So I'm going to subtract 12x minus 60, leaving me with 71. So I have a remainder of 71, and that's it. By the way, if the thing I'm dividing by, the divisor, is of higher degree than linear, so possibly quadratic or cubic or something else, that remainder could have variables in it. It could have to have variables in it. I may not be able to get a constant remainder, but we are going to show in the next video that in general, I can always divide any polynomial by any non-zero polynomial here and get a quotient and a remainder where the degree of the remainder is less than the degree of the divisor. We'll prove that in the next video.